All right, let's jump right in. Today, we're tackling one of the absolute most fascinating molecular characters in all of organic chemistry, benzene. We're going to break down its functional group chemistry to really unmask what this compound is all about. Because you see, benzene isn't just some random arrangement of carbon and hydrogen. It's a structural marvel, and it has this wild, distinct duality to it. On one hand, it is beautifully symmetrical, incredibly stable, and literally the backbone of so much industrial chemistry. But on the other hand, it harbors a really dark side that is incredibly hazardous to human health. It's a true two-faced molecule, and in today's explainer, we're going to break down exactly why that is.
Okay, let's dive into this. Here is our roadmap for the explainer. We'll start with the rules of aromaticity, then move into anatomy and properties. Check out the dark side regarding its toxicity, look at synthesizing benzene, and finally, preparing alkyl benzenes.
Section 1. The Rules of Aromaticity. Discovering Huckel's Rule.
So, before we can really get a grip on benzene, we have to understand the exclusive club that it belongs to, the aromatic hydrocarbons. And to get into this club, a molecule has to pass a very specific, strict theoretical threshold known as Huckel's rule. You can't just take any hydrocarbon with alternating single and double bonds and call it aromatic. Huckel's rule lays out a distinct set of mathematical and physical properties that act as the ultimate bouncer to the aromatic elite.
And here are the 3 strict criteria that Bouncer's looking for. First off, the compound has to be a closed cyclic structure. Second, it must contain exactly 4n plus 2 pi electrons, and n here is just any whole number, 0, 1, 2, and so on. So practically, that means a ring must have exactly 2, 6, 10, or 14 pi electrons, absolutely no exceptions. And third, the compound has to be perfectly coplanar. It needs to lie completely flat. If a molecule misses even one of these 3 criteria, access denied. It is not aromatic.
And this brilliantly illustrates exactly how the rule works in practice. Let's compare benzene to cyclobutadiene. Benzene is a flat, cyclic structure and it has exactly 6 pi electrons. Since 6 perfectly fits our 4n plus 2 formula when n is 1, it passes the test. It's highly stable and it's aromatic. Now look at cyclobutadiene. It's a ring, sure, but it only has 4 pi electrons. 4 simply doesn't fit the formula. So cyclobutadiene fails Huckel's test and is absolutely not aromatic.
Section 2. Anatomy and Properties. Benzene's unique personality.
Now that we know the rules of the club, let's look at the physical reality of the molecule itself. Benzene is this perfectly flat, regular hexagonal shape. It uses sp2 hybrid orbitals to bond its carbons together. But here's the really fascinating part. Every single carbon-carbon bond in that ring is exactly 139 picometers long. Now normally, single bonds are longer and double bonds are shorter, right? But in benzene, because those pi electrons are shared entirely around the ring, every single bond distance is identical. So the crucial point is, this proves its perfect continuous symmetry.
Because of this incredibly stable structure, benzene has a very distinct personality in the physical world. At room temperature, it's just a colorless liquid. It is highly flammable, and if you burn it, it gives off this thick, sooty yellow flame. But interestingly, it has a very distinct, almost sweet smell. It's actually the chemical responsible for that sharp, kind of nostalgic aroma you catch at petrol stations, thanks to its high octane number. It's also lighter than water, nonpolar, and it's a staple in common household items like paints, glues, varnishes, and thinners.
Section 3. The dark side, toxicity, and health impacts. All right, this is where our story takes a stark, dramatic turn. Because despite its sweet smell and how incredibly useful it is in industry, benzene is profoundly dangerous, and the scientific consensus on this is absolute. Both the U.S. Environmental Protection Agency and the World Health Organization's International Agency for Research on Cancer have officially declared benzene a known carcinogenic compound. There's no debate or ambiguity here. Long-term exposure to this solvent is a direct, severe threat to human life. Now, what's really interesting here is the exact biological mechanism of this toxicity. And honestly, it's terrifying. When benzene gets into the human body over a long period, like a year or more, it targets the blood and bone marrow. The body actually accidentally oxidizes the benzene, which produces an epicoid, and this epicoid is highly reactive and carcinogenic. It goes in and directly interacts with your DNA. This leads to a drop in red blood cells, anemia, and ultimately a fast-moving, devastating cancer known as acute myeloid leukemia.
And we can't ignore the short-term effects either, because inhaling high levels of benzene is just as alarming. Direct contact with your eyes, skin, or lungs causes immediate tissue damage. And inhaling the fumes, it triggers this rapid-fire cascade of terrifying symptoms. We're talking severe vomiting, stomach irritation, intense sleepiness, splitting headaches, physical tremors, and eventually, total unconsciousness. At high enough concentrations, acute inhalation can quite literally be fatal.
Section 4. Synthesizing benzene, the origin story.
Okay, let's step safely out of the danger zone and back into the laboratory to see how chemists actually build this molecule from scratch. The textbooks lay out 5 primary synthetic pathways for benzene. We've got the aromatization of aliphatic hydrocarbons. We can use the cyclic polymerization of ethene. There's the decarboxylation of sodium benzoate. We can do a reduction of phenol. And finally, the reduction of benzene diazonium salts using hypophosphorous acid. And having all these different pathways is absolutely crucial. It means chemists can synthesize benzene no matter what raw starting materials they happen to have on hand.
Let's move to a specific example and see how this builds in practice. This is a really elegant one, the reduction of phenol. Step 1, you take phenol vapors. Step 2, you pass those vapors over heated zinc dust. Under that strong heat, the zinc acts as a super powerful reducing agent. It literally just rips the oxygen atom right off the phenol ring. And that leaves us with our perfectly formed benzene ring, along with a byproduct of zinc oxide.
Now, once we have synthesized that core C6H6 benzene molecule, an entirely new world of chemistry opens up to us. By just replacing one of the hydrogen atoms on that ring with an alkyl group, something like a methyl or an ethyl group, we create derivatives known as alkyl benzenes. And this completely resets our framework, because these derivatives are incredibly important aromatic compounds in their own right, used everywhere in chemistry.
Section 5. Preparing alkyl benzenes. Building derivatives. So the obvious question is, how do we attach those side chains to the core ring? Well, just like with building benzene itself, there are several distinct methods to prepare these alkyl benzenes. First, we have Friedel-Crafts alkylation, which is a total classic. We have the Wurtz-Fittig reaction, and we also have reduction methods, specifically the Wolff-Keshner reduction and the Clemmensen reduction. The Clemmensen one, for example, uses a zinc amalgam and concentrated hydrochloric acid to reduce aldehydes or ketones straight into alkyl groups, right on the ring.
But you might be wondering, why so many different methods? Why not just use Friedel-Crafts for the whole shebang? Well, it comes down to precision. Friedel-Crafts is super useful, but it has a notorious flaw. The alkyl groups often spontaneously rearrange themselves during the reaction, which gives you totally unexpected products. By opting for the Wolff-Keshner or Clemmensen reductions instead, chemists can reliably build these complex alkyl benzenes exactly how they design them on paper, entirely bypassing those unpredictable structural rearrangements.
And that brings us to the end of our journey today. We've explored the strict, almost magical mathematical rules that give benzene its identity, its perfectly symmetrical anatomy, its crucial importance in industrial synthesis, and of course, its terrifying toxicity. And I think it leaves us with a really provocative question to ponder. How can a structural marvel, something so perfectly symmetrical and so utterly vital to the foundation of organic chemistry, also be so inherently hazardous to human life? It really is the ultimate paradox of the chemical world. Thank you so much for joining me for this explainer, and as always, keep questioning the science around you.